is Chakos is a PhD candidate at the University of Toronto. He holds an MSc degree from University of Toronto and a BSc degree from University of Athens. His research interests include deep learning and data management. And his talk is titled Video Monitoring Queries. Okay, so I think the next step is I'm going to play the video. Okay, so can everyone see the video? See the screen?
Yes.
All right, cool. So let me play this video.
This is a joint work with my collaborators in University of Toronto. I will begin this talk with motivation and contributions to this work. Then I will demonstrate our solutions to important challenges. Finally, I will present the experimental results of our work. Or to find the best days to begin the construction, finalizing the draft. Additionally, events such as attempted burglaries or traffic accidents can be identified instantly. We now present a series of features of video model queries such as special constraints and counterfeits. We demonstrate high performance accuracy due to amplified activation effects by regulating the class activation. Various reduction techniques for aggregate queries involving spatial pre-predictive that effectively reduce the values of the estimates. Our filters dramatically increase the free processing rate and speed up pre-processing by at least orders of magnitude in real application scenarios. We answer video queries by using deep neural networks. First, we are processing the frames and extract their features. Then, we use extracted features to make our predictions. Predictions to other queries, such as count estimation, plus count estimation, that counts all of the objects of the specific task in the frame, such as current task. And crowd motor applications in which frame may contain multiple hundreds of or thousands of objects, such as sport events, demonstration, and political party rallies, and many more, are not focused for our work. Finally, we validate spatial constraints by comparing the location of two. For example, we have spatial constraints that identify cars on the right side of the buses.
Hi all, today I'm going to talk about video monitor queries. This is a joint work with my collaborators in the University of Toronto. I will begin this talk with motivation and contributions of this work. Then I will demonstrate our solutions to important challenges. Finally, I will present the experimental results of our work. They are produced more data than ever, but more recently we saw a huge increase on the amount of visual data, such as images and videos. Surveillance cameras is one of the main reasons of this sharp increase in video recordings. Every major city has hundreds of thousands of cameras. There are cameras at homes, at stores, and many more places. The main goal of our work is to create a framework to analyze the huge volume of video data. In that direction, our work complements recent works by contributing new query types such as count, special constraints, and aggregate queries. With high volumes of data and frameworks to analyze them, now a construction company, for example, can utilize the data in order to plan for further road expansions or to find the best dates to begin the reconstruction by analyzing the traffic. Additionally, events such as attempted burglaries or traffic accidents can be identified instantly. We now present a series of filters of video monitor queries such as special constraints and count queries. We demonstrate high performance accuracy due to amplified activation effects by regulating the class activation map. We present variance reduction techniques to process aggregate queries involving spatial query predicates that effectively reduce the variance of the estimates. Our filters dramatically increase the frame processing rate and speed up query processing by at least 2 orders of magnitude in real application scenarios. We answer video queries by using deep neural networks. First, we are processing the frames and extract their features. Then, we use extract features to make our predictions. Finally, we utilize the network's predictions to answer queries such as count estimation that counts all the objects in a frame, class count estimation that counts all the objects of a specific class in a frame, such as a car class, and crowd monitor applications in which frames may contain multiple hundreds or thousands of objects such as sport events, demonstration and political party rallies, and many more are not the focus of our work. Finally, we evaluate spatial constraints by comparing the location of 2 or more objects. For example, we can have spatial constraints that find cars on the right side of the buses, as you can see in this example. The basic idea of filtering is to discard frames that are not relevant to the query at hand, as depicted on this example. Frames are passing through a cheap approximate filter, which is trained to predict explicitly some query, such as count query. After the evaluation, the associated probability of the frame is compared with the preset threshold. Frames with higher score are further evaluated by state of the architecture, while the rest of the frames are discarded. The discarded frames are not processed further. That way, the expensive image analytical algorithms like MaskRNN are invoked with enough confidence that the relevant frame information will be discovered. The main challenge of this work is to create fast and accurate filters that can answer a variety of queries. We achieve the first by alternating the image classification and object detection framework by removing unnecessary overhead, such as the bounding box framework. Instead, we utilize an alternative approach to locate objects using class activation maps. For the latter, we utilize the class activation maps and amplify the activations via training. In the next slides, we present our proposed filters as well as sample outputs of class activation maps. In this slide, we present the first filtering approach. The image classification filter is inspired by image classification algorithms. We utilize a pre-trained image classification network, such as VGG19, and use it as backbone network in our architecture. We then extract the feature maps of the 5th layer of the network. Experimental results show that the 5th layer provides the best trade-off between prediction accuracy and time performance. We also extract the weights of each object class acquired by the full connected layer, as we can see in the architecture overview. By multiplying the feature map and the weights, we obtain the class activation map for each object class, and transform it to a grid map of n by n cells by fitting the map into the frame size. We can find the position of the objects in a frame by thresholding the grid cells and subsequently answer spatial constraint queries. To answer a count query, we calculate the count of each object class. by using an n-dimensional vector of foreign classes. For the object detection filter, we use a similar approach. We have created a hybrid algorithm by utilizing the capabilities of object detection without the unnecessary overhead to discover the object's exact position. We utilize Darknet, a network from DL Framework as backbone network, and extend the architecture by adding a branch in a specific layer of the network. The intuition for this architecture is to utilize the convolutional layers learned from the backbone network, but instead of using them directly to predict, we extend the architecture by adding a branch that uses the regularized heatmap to pinpoint grid cells that contain objects. The added branch has a predefined network architecture that consists of 3 convolutional layers, followed by a global average pooling layer, and finally, a fully connected layer, and supports both object localization and count estimation approaches. The branch input is the feature. The branch's input is the feature map of the layer that the branch is placed. Placing the branch at higher layers introduces a trade-off. Processing time per frame increases since frames need to pass through more layers. On the other hand, accuracy increases. Despite the higher accuracy, placing the branch to higher layers reduces the grid map's resolution. That may result to lower object localization capabilities, despite the more accurate features obtained. We present an example of potential grid map. This grid consists of 8 by 14 cells. The red cells indicate location that the object has been found. To find cells that include objects, we first threshold each cell. Each cell has an associated score that describes how probable is an object to be present in this cell. After we pinpoint the objects in the frame, we can compare their locations using the cells as coordinates. In this example, we know that the man in red is on the left side of the woman in black, based on the grid cell's position indicated with red color. If a frame consists of objects of multiple classes, then we will have multiple grid cells, one for each object class, for a single frame. However, since the frames of a specific size, each grid map will have the same size across different object classes. Thus, comparison between objects of different classes can be made the same way with objects of the same class. This slide showcases the class activation maps as a heat map for different images classified by containing a human object class. Class activation maps localize objects as they highlight object locations most influential in the classification. This approach can capture any possible spatial constraint, since each predicted object has specific coordinates. As a result, we can compare the location of objects of the same or different object class with a simple coordinates comparison. Object presence, along with spatial constraints, offer numerous avenues to express temporal aggregate queries of interest. This query reports a number of frames in a branch window of 5,000 frames, for which a black car has a stop sign on its right in a road surveillance scenario. From a query evaluation perspective, we can utilize a sampling-based approach to evaluate for all objects present in the frame. We utilize a state-of-the-art object detector such as MascRCNN to perform object localization. Then we can determine if the sample frame satisfies the query constraints. Essentially, for each sample frame, we determine a value that can be utilized in conjunction with sample-based approximate query processing techniques to derive statistical estimates of interest, such as mean values and variance of estimates. We now present part of the results of the experimental evaluation of the proposed approaches. We utilize 3 different datasets, namely Coral, that consists of a single human class, Jackson, that has 2 classes, car and persons, while D-Track, that consists of cars, trucks, and buses. We extract the labels of every dataset using MascRCNN with recent 50. Additionally, MascRCNN is our baseline for our experimental setup, which has accuracy equal to 100%. As we can see, MascRCNN takes 4 to 7 hours to produce predictions for a single dataset. We use stochastic gradient descent with momentum to train our object detector and random optimizer for image classification approaches. We trained Coral and Jackson dataset for 5 to 10 epochs, and for 3D tract, we require 10 to 20 epochs of training to achieve optimal performance. First, we show the class count evaluation across 3 different datasets and compare image classification and object detection approaches. We observe that the two techniques perform equally well. Image classification techniques perform much better when considering exact counts, but both techniques present similar accuracy for approximate counts within count 1 or count 2. It is worth noticing that both approaches present higher accuracy for classes that are less popular, even though the less popular classes in the video streams are represented by less training examples. However, less popular objects in frames have typically lower counts in each frame. They thus represent an easier estimation problem. Next, we show our experimental results on object location estimation. Object detection localization techniques perform much better, as they are optimized for object location prediction because the backbone network's feature maps provide more details regarding the spatial and location features of the objects in the image. We also observe that less popular classes have lower F1 score, and this is an artifact of training, since real videos contain unbalanced object classes. Less training examples result to lower location optimization accuracy. Another reason is that predicting location is a much harder problem than predicting counts. We now present an evaluation of the effectiveness of these filters in a query processing setting. We present 3 out of the 7 queries we tested in our framework. For these queries, we progressively enable all the applicable filters, and for the frames that pass each filter, we evaluate them with an object detector, such as multi-modal, for the final evaluation. All the queries achieve 100% accuracy. We can obtain lower processing times by reducing the accuracy of the queries. It is evident that performance advantages offered by the filters proposed are very large in comparison with our baselines, since we achieve speedups of at least 2 orders of magnitude. We have presented a series of filters to estimate the number of objects in a frame, the number of objects of a specific class in a frame, as well as to assess an estimate of the spatial position of an object in a frame, enabling us to reason about spatial constraints. We also demonstrate the aggregate queries evaluation framework. These filters, when applied in real application scenarios, they achieve dramatic speedups by several orders of magnitude in comparison with traditional state-of-the-art object detectors, such as multi-modal. This work opened numerous avenues for further study. Thank you.
Hello, everyone.
All right, so thanks, Yanis, for the very interesting talk. I'm looking at chats right now, and so far I don't see a question, but feel free to ask anything here. So I have a question. So I think this was very interesting. This is a very interesting work. I noticed that the queries are, so one question I have is, how much variety of images can you handle? So so at some point, you might be monitoring traffic data, but at some point, if I give you some totally different images, then do you see any issues on extending your current system to new types of images?
Hello, that's a very interesting question. I think that you mean the concept drift. That is a thing that when the domain of the data is changing, we need to adapt. And no, in this work we cannot do that, but we're planning to do that in future works, and it's a very interesting domain to work. The issue here is that the training data is static, so we cannot adapt in new object types. I mean, we can have either domain problem. If, for example, we don't have black cars in the training example, we cannot recognize black cars, but we cannot find difference such as a road that has changed to a street walk. So we cannot find the difference between a road that that cars are passing through the road or humans are passing through the road. So it's an interesting problem to solve. in the future.
All right, thank you. So maybe I can ask one more question. So it's very interesting you're using SQL queries here. So that really piques my interest. So maybe this can be extended to support joins in queries as well. And so are you envisioning some kind of query optimizer in the future where we can be very declarative and it sort of optimizes how to process the videos in the most efficient way?
Yes, of course. The query optimizer is necessary to this works because in the future we may need to have multiple filters that they need to optimize in a pipeline. So in our future works, you will see something like a query processor. And of course, the query language is important, but it's not the main aspect of our work, but it's very important for a framework.
Okay, thank you. So if we don't have more questions, let's move on to the second talk. So while Alan is helping us prepare, let me introduce the speaker. So Shang Yu received his bachelor's degree in computer science and technology from Tsinghua University in 2017. He is currently a PhD student in the Department of Computer Science, Tsinghua University, Beijing, China. His research interests lie in machine learning for database and crowdsourcing data management. So today, he will give a talk titled Reinforcement Learning with Tree-LSTM for Join Order Selection.
Hello everyone. Today, I will introduce our work reinforcement learning with Tree-LSTM for join order selection. As we all know, the optimizer is an important part of the database. The user enters a query, and the optimizer needs to output the query plan and give the plan to the database for execution. In the optimizer, there are two components that are very important: the plan enumeration and the cost model. In the plan enumeration, some methods is used to enumerate the possible query plans. Cost model is responsible for estimating the cost of these selected plans. Finally, the optimizer selects the best plan as the return result based on the cost model estimation. The accuracy of cost estimation has always been a problem that we are studying. It is difficult for us to estimate the cardinality correctly. At the same time, the parameter of the cost model relies on the environment and often needs to be set by the DBA. Given a cost model, many methods have been proposed to reduce the search space for join order selection, but they often face a trade-off between speed and cost. To recent works, DQ and Rejoin have been proposed to use deep reinforcement learning to reduce the search space. Similar to DP, we first described this process as a Markov decision process. The optimizer is an agent, a join is an action, the environment is the cost model or database, the reward is our cost or true latency, and the state is our join order. The picture on the right describes this Markov decision process of the join process. In the beginning, we have the initial state of 4 independent tables. Each time we select 2 tables to join, we get the intermediate state. After 3 join actions, we get the final plan. That is the termination state. In all parts of deep reinforcement learning, policy function is very important. The agent uses it to choose one join action according to the state each time. The input is the state, the output is the action. The policy function, it uses a neural network to estimate the cost of the subsequent state produced by each join operation. We can find that the role of the neural network here is very similar to the cost model. Suppose there are n relationships in the query. We can find that the Markov process of dynamic programming needs to check an exponential search space. However, each time the policy function of the DRL only needs to estimate n possible states, a total of n1 times the policy function is performed. So DRL only needs to check the search space at the polynomial level. At the same time, the results indicate that they can give a competitive join order in the cost model. However, although the previous 2 algorithms gave competitive results on cost, they did not give satisfactory results on latency. Let's recall two learning strategies, learning from demonstrations and learning from rewards. LFD is the method used in DQ, using the good join order generated by DP to pre-train the model, so that the model can generate join order like DP. LFR, it means that we are constantly exploring different orders and using feedback for training. Both good orders and bad orders will be considered. The LFD learning space is very small, while the LFR learning space is very large. But when considering latency, the low-cost solution might be bad, so we need to learn from feedback. That is learning from rewards. Let's observe the representation of join states by DQ and rejoin. DQ uses a length n of 0-1 code to indicate the status of the join tree. Each position 0 or 1 indicates whether the table has been joined. Rejoin is similar to DQ, and also uses a length of n encoding, but we do not use 0 or 1, but use hide information in the position of each table. But we can find that the vectorized representation of DQ and rejoin will cause different join orders to produce the same representation. The same representation in the neural network means the same output. If a good order and a bad order produce the same representation, then the neural network cannot correctly estimate the input state as good or bad, thereby making a wrong choice. Besides, a fixed length vector is hard to expand when schema changes or multi-aliases occurs. A more powerful neural network is needed. We recall the method of the two previous work. They all use a vector as a feature to represent our join tree structure, and then do the neural network. We should directly input the join tree into the neural network for calculation. Here we find that Tree-LSTM can be used to solve this problem. Here we will bring the goal of our RTOS. One is the latency goal, and the other is the dynamic feature goal. The goal of latency is that we hope to find a better join order on latency, get rid of the constraints of cost model, and produce a better join order than DP. The dynamic goal is that we can support some dynamic operations on the neural network. For example, adding a table, or operations like multi-aliases. This is our RTOS framework. We can see that we can get an initial state by entering a query. Each time, we first check the state. If it is an intermediate state, we generate a state space based on all possible join operations. The state space is each corresponding possible next state. We use Tree-LSTM to estimate each state. Action selection will select the best join action according to the estimation of Tree-LSTM for each state. If it is a terminated state, it means that we have obtained our final join order. At this time, we input this join order into the database. The database executes the join order, so as to obtain the latency we need as feedback. We send these feedback to the memory pool for recording, then use them to train our neural network. There is a special point here. We said before that we want to use latency for training, but feedback still has a cost. We will explain this part later. We have proposed RTOS, and we use Tree-LSTM to capture the structure information of the join order. Here we will explain the 5 main representations and their corresponding meanings. Query representation, record all target join information. Column representations, record the column information, e.g. selectivity of the filter predicate. Table representations, record all columns information in this table. Tree representations, record the state of join tree, composed of tables. Forest representations, composed of several trees. State representation, represent an intermediate state, composed of forest and query representation. Let's take a detailed look at the neural network part. The first is the query representation. We use an NN vector as the input vector of the network to represent the join relationship. 0-1 indicates whether there is a join between the two tables. Then we observe the table and column representation. The column representation depends on the predicate. According to the specific predicate, as the input feature, we get the representation of each column. When all the columns in a table are pooled, we get the table representation. Next is the most important figure C. We first represent each join tree. Since the join operation distinguishes between left and right tables, we use n-ary units. The n-ary unit will perform a transformation for each position. For the representation of forest, because we do not distinguish the order of each tree, we directly use the child sum operation to sum all the inputs of the join tree and then calculate. Finally, we connect the forest representation and the query representation to get the representation of our intermediate state. The above only defines a method for constructing a neural network for the input tree structure. The true neural network connection is only constructed when a joined tree is given. We use deep first search to describe this process. We only build the n-ary node after we get the required table and column representations. Therefore, any tree structure can be input. We do not need to limit the size or node. We use dynamic pooling to support dimensionality reduction for features of different sizes. Here we talk about how to handle the schema change and multi-aliases. The key in representation is the column representation. When we add a table T, we assign new column parameters for T, and also use DFS to build the neural network. We fix other tables' column parameters, and only train parameters for T. Multi-aliases can be viewed as adding a copied table, which is much easier to solve. Share column parameters of T for different aliases to get representations. Here let's reconsider the cost and latency. When we use cost as a reward, we only need a few milliseconds to get feedback, but when using latency as a reward, it takes a few seconds, or even a few minutes to run this join order to get feedback. And training a DRL optimizer often requires a lot of training data. For example, 20,000 episodes. One episode means once RL process. Therefore, simply using latency as feedback brings huge time overhead for training. However, our goal is to get good performance on latency. We need to get enough training data in a short time. Cost is an approximation of latency. We can use cost to generate a lot of training samples. 2 steps training is proposed to save the training time. First, we do cost training. By using cost as feedback, we collect a lot of training samples. These samples will help DRL distinguish many bad and good plans. Second, we do latency tuning. We collect both cost and latency to fine-tuning the model. Use a small amount of training to correct the wrong estimate in cost training. Here we introduce RTOS settings. RTOS is implemented on PostgreSQL and improves the join order part of a query plan and leaves the others, e.g., access methods such as hash join or index join, for PostgreSQL to decide. We use DQN as the DRL method. Epsilon greedy is used to discover new orders. We use the following method as the baseline. DQ, rejoin, previous DRL methods, we re-implement them according to the paper. SkinnerDB, the latest method, that chooses a good join order according to the RL policy. It relies on its customized in-memory execution engine. We compare with the join order finally generated by SkinnerC. The last two are dynamic programming and quick pick. We use 2 datasets for testing. Job and TPCH. Job is a real-world dataset based on IMDb to provide a realistic workload. It has 113 queries from 33 templates. It has 3.6 GB data, 11 GB when counting indexes, and 21 tables. The number of relations in each query ranges from 4 to 17. TPCH is a standard industry database benchmark with 8 tables. We have generated 4 GB data and 110 queries from 22 templates. We first verified the effectiveness of the cost. According to the experiment, we found that in the collection of 20,000 episodes, we spent 10 hours to collect latency, while cost only took 0.05 hours. At the same time, we also found that during training, when we want to get the same effect as dynamic programming, 2 steps take more episodes but less training time. Then we observe the cost experiment. We choose dynamic programming as standard. The cost is normalized by the latency of dp. 1 means equal, lower is better. We find that RTOS outperforms all other methods on job and TPCH and close to dp on job. The RTOS exceeds the DQ paper result of 1.31, which pre-trained from dp's plan. The number of relations in TPCH queries is usually small, which leads to small search space. All methods can generate good plans. Then we observe the latency experiment. We also choose dynamic programming as standard with geometric mean instead of arithmetic mean. We find that RTOS still outperforms all other methods on job and TPCH, and even perform better than DP. SkinnerC, according to his, the in-memory execution engine produces a good join order, which is not necessarily suitable for PostgreSQL. We further grouped queries by their template id. We can see that for all templates RTOS can almost generate the plan no worse than DP. SkinnerC and RTOS are obviously better than DP on template T20, T26, T28, T29 and T31 which have multi-aliases in these queries. This proves RTOS can handle multi-aliases well. We also grouped queries by their template ID to show results for TPCH. Many of these templates have less than 3 relations in their queries, which make the results the same for all methods. We did not show them to have a better view. We can see that for all templates RTOS can generate the plan no worse than DP. Thank you for listening. Questions are welcome.
All right, so thank you for the nice work. I have one question from the audience, so let me read it. Did the experiment test more size of TPCH, such as 100 megabytes, a gigabyte, 10 gigabytes, and 100 gigabytes? So.
Okay, can you hear me? Oh, okay. Hey, okay. I have tested the different more size of TPCH, but I only tested for 1 GB, but I didn't test for the 10 GB and 100 GB or and so that it's but when I do the experiment on 1 GB, the results seems similar, but so I didn't do more experiments because the too large database is will take a long time for we to get latency, and which results in the experiment get too hard. Yeah.
Okay, thank you for the answer. So another question, how is the reward function defined in the RL model to be a good feedback for accuracy?
Okay, it's the latency. We use the latency as a reward, so we didn't get any reward for each step. Just and for example, you can view it that we set the reward of each step is 0, and then we just set the reward as the latency when we get the her join plan. So.
Okay, so thank you very much for the answer. So I think, thanks very much again for the nice work. I think we can move on to the next talk then.
Okay, so, thank you very much.
Thank you. So the next speaker is, I hope I'm pronouncing it correctly, Shohedul Hassan. So he is a 4th year PhD student at University of Texas at Arlington. So today his talk is going to be on approximate query processing for data exploration using deep generative models. So Shohedul, please take it away. Actually, we're going to show you.
Hello everyone, welcome to my presentation. I'm Shohedul Hassan from University of Texas at Arlington. In this talk, I am going to present our work on approximate query processing for data exploration using deep generative models. Other collaborators in this work include Saravanan, Nick Kodas, and Gautam Das. In this presentation, I will discuss how deep learning can be useful in approximate query processing. And specifically, I will talk about 3 things. First, how deep generative models can be used to generate samples. And if the generative models are not accurate, how can we reduce the bias? And how to increase the estimate accuracy through ensembles. And finally, we will show some of our experiments to demonstrate the effectiveness of our approach. Now, let's start our main presentation. Data-driven decision-making has become a key to success in today's competitive business world. However, data has been generated at an unprecedented rate, which makes exact data analysis extremely expensive. Think about a scenario where a data scientist wants to perform exploratory data analysis on flights dataset. She issues a lots of queries like what is the average number of passengers on flights starting from Texas. As she is interested in interactive data analysis, she is happy to sacrifice a fraction of accuracy for the sake of speed up. For these kind of scenarios, approximate query processing or AQP is a promising technique that could give approximate results in a fraction of time needed to answer it exactly. But how can we perform AQP? One traditional approach is answering the queries from pre-computed samples. The problem of this approach is these pre-computed samples are often insufficient for accurate results. Another traditional approach is answering the queries from on-demand samples. The problem of this approach is this suffers from high latency. Now the question is how to solve the age-old dilemma of inaccurate results and expensive step of going to the database. Can we do better in sample-based AQP without continuous pressure on database? In our work, we use deep generative models to learn the data distribution faithfully. Once the model is learned, we can generate as many as sample we want. Using these samples, aggregate queries can be performed using existing AQP techniques. Now, we'll discuss three main problems in very high level. First, how can we select an appropriate generative model? Suppose somehow we have selected the appropriate generative model. If that model is not accurate, then how can we reduce the bias? And then, how to increase estimate accuracy through ensembles? Let's talk about the first one. There are several challenges in deep learning based AQP. One of the key challenges is finding a suitable deep learning based distribution estimation approach, which can really learn the underlying data distribution. The learned model should be very lightweight, and it should not take a lot of time in training. Moreover, we cannot make any prior assumption about the data characteristics. By keeping all of these challenges in mind, the question is, what kind of deep generative model we should use? We have found that Variational Autoencoder is very effective for this purpose. It's very lightweight, only a few hundred kilobytes, and it does not take a lot of time in training, only a few minutes. Now let me briefly talk about Variational Autoencoder. Variational Autoencoder or VAE consists of two pairs of networks. One is encoder and another one is decoder. The encoder transforms the input into a low dimensional dense representation, which represents the data characteristics. And then the decoder converts the latent representation to original input space. Once the model is learned, we can draw sample from latent space. And the decoder can convert the sample in latent space to sample in original space. Now, if I give the decoder to user, the user can generate as many as sample she wants without putting any pressure on database. But unfortunately, the naive use of VAE will not be good enough. These seriously suffer from model bias. Model bias happens when the samples are not representative of underlying dataset. Aggregates generated over these samples are biased estimate. And we should not be happy with biased estimate, and it should be corrected. Now the question is, how can we reduce the bias? In our work, we advocate for variational rejection sampling to reduce the bias. We will accept a drawn sample if the associated probability is less or equal to acceptance probability. Else we'll reject it. We will resample until this condition is met. The parameters of variational rejection sampling are learned by optimizing an evidence lower bound. In short, we call it RLBO. There is one important parameter in variational rejection sampling, which is called threshold parameter T. It determines the quality of sample. It also determines how much time sample generation will take. The details are discussed in the paper. We would recommend you to read the paper if you are interested to know more. Now, if one VAE model can approximate the data distribution, then multiple VAE model should learn even finer characteristics. In our work, we use an optimization formulation that splits the dataset into k disjoint partitions. And then we learn one VAE model for each partition. And eventually we can learn even finer characteristics. But how can we partition the database? Should we do it arbitrarily? Typically, especially in OLAP settings, tuples are often grouped according to hierarchies on given attribute. Such hierarchies often represents meaningful groupings. So definitely we can partition based on those meaningful groups. For example, we can partition based on location. But what will happen if the number of such atomic groups are really high? For a given k, how can we partition them optimally? In the next slide, we will briefly describe optimal partitioning for OLAP hierarchy. Suppose we are given a tree as a form of OLAP hierarchy. Now, where each leaf represents one atomic group, and we know the RLBO value of every node. We use dynamic programming to split this tree into k partition. It's a pity that we don't have enough time to discuss the details. But if you are interested, we would recommend you to read our paper. There are some other cases which you may find interesting. So far, we have only talked about the processes. Now let's talk about the performance. We have conducted extensive experiments to demonstrate the effectiveness of our approach. We have used two datasets, sensors and flights. Both of them are quite challenging for AQP due to their complex correlated attributes and conditional dependencies. We have used IDE benchmark to generate queries. From those queries, we have selected 1,000 challenging aggregate queries. We generated 1% fixed sample from the real data set, and we also generated a sample in our approach. And then we use those queries to get the estimate, and we calculated relative error for each type of sample. The absolute difference of these two relative error is our performance measure. In one of our experiments, we show comparison among latest deep learning based AQP techniques and traditional AQP and our VAE based approach. And clearly, our VAE based approach is outperforming the other techniques. In another experiment, we show that if we increase the sample size, the performance improves, which is also the case for AQP in general. Even with 0.5% sample as training data, our performance is quite impressive. This is another perspective on our approach. If we vary the selectivity, with the decrease of selectivity, the performance degrades, which is also the case in traditional AQP. But for high selectivity, our performance is really impressive. And even for the low selectivity, we can improve the performance using multiple VAE models. This plot shows the impact of rejection sampling. If the threshold parameter T increases, the quality of samples decreases. And the sample generation time also decreases. So it's up to user what kind of sample she wants to generate and how much time she has. Based on that, she can set the value of T. Finally, we show that if we can wisely partition the data, then the performance definitely increases. There are a number of interesting things that we can work on future. For example, how can we generate sample under constraint using deep generative models? It will be also interesting to see the application of generative models to generate synthetic samples in other data management applications, such as structured and knowledge graph. If you want to know more about variational rejection sampling, we would recommend you to read this blog from the authors of Variational Rejection Sampling. And this concludes my presentation. And thank you very much for listening the talk. Thank you.
Okay, so thanks, Shoedul, for the interesting work. There are a couple of questions here. Let me just read the first one. So you said that training takes a few minutes. On what size of data and what's the size of the model in bytes? And another question for clarification, if I train a model over G attributes, when I sample the model and decode the sample, am I expecting to get a tuple of G elements?
Thanks, Steven. So the first question was how much the training training takes, how much time training takes. So it takes less than 5 minutes, and for 1 million tuples, the model size become like 200 kilobyte or something like that, 300 kilobyte. Yeah, and the next question was, if I train a model over G attributes, when I sample the model and decode the sample, I'm expecting to get a tuple of G elements. And okay, so yeah, this is true. So if the input has G attributes, then the output will be also G attributes. We are generating fake samples, which will have the property of data distribution. As a result, the approximate query will be similar. And there is another question: where does K, the number of partition needed, come from? More generally, can you not learn the right K that would optimize the ultimate goal? Generally, 1K is good enough. But if the data represents such property that you can partition based on a particular attribute, then you can partition the data. And we are not giving what K we should choose. Rather, if someone gives us the K, then we can partition the data. Finding the right K is itself a challenging problem and can be a future direction. And how many samples in percent you needed for the experiment you presented? Just 1% sample we have used, And for one of the experiment, we have varied the sample from 0.5% to 5%. And then another question from Dhruv, for a given query, was there only one deep generative model chosen? How do you rank the models if multiple deep generative models can be used for a query? So we are training a model which can generate samples. So whenever you give a query, the queries will be answered from those samples. So basically we are not training a model for a query. Rather, from the samples using the existing AQP techniques, you can answer any aggregate query. Then another question, if you are learning the distribution of the data, cannot you use the directly instead of producing samples? Let me read the question again. If you're learning the distribution of the data, cannot you use the directly instead of producing samples? Okay, so the main problem of using samples directly from the database is sometimes those samples will not be good enough to answer all type of queries. And if you want to use on-demand samples, as I said, like it will take a lot of time. So that's why we wanted to find a way which will generate samples in client side without bothering the database at all. That was actually our main purpose. Yeah, so this is actually a complementary approach which is very efficient and very accurately it can estimate the aggregate queries. That was actually the main purpose. Thank you.
All right, awesome. Thanks so much for going through the questions so quickly. So let's move on to the next talk. So let me introduce the speaker. So Fotis Sava is a PhD student at the University of Glasgow. So the title of the talk is Surf Identification of Interesting Data Regions with Surrogate Models. Okay.
Hello everyone, my name is Fotis and today I'll be presenting our paper called Surf Identification of Interesting Data Regions with Surrogate Models. I'll start by defining what regions are and then defining the problem of identifying subregions. I'll then describe a baseline solution and the complexity of this solution. I'll then reformulate this problem as an optimization problem and then show how we use multi-modal optimization algorithms to solve such a problem. I will then describe the use of surrogate functions to imitate the backend analytics system that helps us alleviate some of the inherent complexity in identifying subregions. And lastly, I will provide some key results on accuracy and efficiency. Let's start by defining what regions are. A region can be defined as a hyperrectangle in a multi-dimensional data space. So in this example, a region is a hyperrectangle in a three-dimensional data space. And formally can be defined as having a center X with side length L, which basically defines the space that is enclosed by this hyperrectangle. A region's interestingness can be inferred by an aggregate statistic computed over the retrieved data points. So for example, using only the included data points, we can compute statistics such as count, average, sum, or variance over any of the associated attributes. So for instance, if we consider x1, x2, and x3 as the values x, y, z that are obtained from an accelerometer, and the aggregate statistic as the ratio for a specific activity, we can see that the hyperrectangle shown here encloses a number of accelerometer readings. And using these enclosed data points, we can compute the number of points that are associated with sitting and infer the region's interestingness. We want to identify interesting regions because choosing to focus on interesting regions can cut down data exploration time. So instead of having the data analyst explore a complete data space, we can help them and pinpoint them to interesting regions that can be considered interesting to crank down on exploration times. Formally, we would like to identify regions which are greater or lower than a user-supplied threshold. In the context of our previous example, this threshold can be, let's say, 30%, meaning that we want to identify regions in which more than 30% of the enclosed data points were generated while performing activity setting. To mathematically express this task, we can think of it as a maximization problem in which we want to maximize the difference between the computed statistic, the aggregate statistic, and the user-supplied threshold. And here f, the function f, indicates the aggregate function which maps a region to an aggregate statistic. In addition to this, though, we also like to have control over the size of a region. So we would like to provide an adjusting tolerance parameter called C, so that the user can increase or decrease this parameter with respect to whether they are interested in identifying large regions or small regions. To solve this problem, we first start with a baseline method. Assume that we need to find a region for a single dimension, in which a center point X, a side length S, and define a continuous interval in a single dimensional space. We can discretize this space such that we have a number of points X and a number of side lengths L, with the sets X and L defining the granularity of our algorithm. And this can be made much simpler by having this example here. If we can consider each red point as a suggested region, which has to be evaluated. So we need to evaluate the objective function for each one of those suggested regions using this discretization scheme to identify interesting regions. The color bar here denotes the value of the objective function. And as we can see from this example here, we need to identify those three regions that seem more interesting with respect to what we've defined as our objective function. However, the problem with this approach is that the number of evaluations becomes exponential with the number of dimensions as a larger space has to be discretized. So for a single dimension, this might be simple as with a small granularity of 20 points, we only have to evaluate we only have to do 400 function evaluations, whereas for 3 dimensions, this number explodes into 64 million function evaluations that will have to be performed over a backend data analytics system. And as you can see, this will take a long time. So we introduce this problem as a multi-modal optimization problem. And as we've seen earlier, the objective function is multi-modal as there could be many regions of interest. In addition, the function f is unknown, its structure is unknown, so we cannot exploit its structure to identify regions more easily. Therefore, our approach was to use low and swarm optimization, GSO, to locate regions of interest. The way this algorithm works is that we initialize a number of particles in random positions, and each particle denotes a region that has to be evaluated. And as you can see, for as few iterations as 10, those particles converge to what we consider as interesting regions. What's more important to notice is that the end positions denote clusters, which shows that the particles in the GSO algorithm only influence other particles within a specified neighborhood. And this allows the algorithm to converge into multiple positions, which allow us to propose multiple regions that could be interesting to the user. In addition, infeasible solutions become stranded and are thrown away. In this example, infeasible solutions are those solutions that are below that user-specified threshold that was provided by the user. However, even with the introduction of the GSO algorithm instead of the baseline solution that we firstly described, we still have the backend analytics system as a bottleneck. So using the GSO, we have successfully reduced the number of function evaluations, and the number of function evaluations that we have to perform is now dictated by the number of iterations and the number of particles that we have. However, we still have to compute the aggregate function over last data. Our solution to this problem was to treat this backend analytics system as a black box function and approximate it using a surrogate model, a surrogate function, which is usually a machine learning model that is trained using past function evaluations. So for instance, you can see here that the backend analytics system takes as input a region and it outputs a statistic Y that is computed using an aggregate function. With the same thing in mind, we can replace the backend analytics system with a surrogate model that is trained using previous queries, but still takes as input a region and outputs an estimated statistic. The difference between the two is that the execution time depends on dataset size for the first example, whereas for our second example using a surrogate model, the execution time only depends on the inference time of the model, and this can be as short as a few milliseconds. Now that we've described our solution, I will proceed to show some of the experimental results that we were able to obtain. However, I'll first explain a little bit of what the task was during our evaluation. We set up a number of artificial continuous regions, where in the first column, in the left column, we have an aggregate statistic which is larger for a single region shown highlighted with the green color here, and where the aggregate statistic is larger for a number of regions as shown in the bottom left example. We also have a different task of wanting to identify regions where there is a large number of points concentrated on the regions enclosed in green. So we can see in both examples that the main task is to identify the boundaries of those regions that are highlighted in green. And the accuracy for both of these tasks is evaluated by the Jaccard Similarity Index, or the intersection of a union, which, to be put simply, defines how much of the predicted region overlaps with the predefined region. So some of our results concerning accuracy are the ones shown here. We compare our own approach called SURF with the naive approach, which uses the discretization scheme introduced earlier. We also compare our approach with an algorithm called Tree, which is an algorithm proposed by Friedman. And we also compare our approach with the GSO algorithm using the backend analytics system. So instead of replacing it with the surrogate model, we leave it as is. And as you can see on the top left graph, Prim and naive perform best, and overall naive performs really well across all four graphs. However, naive performance makes it a less tractable solution, as we will see later on. The main point to consider in all of those graphs is that SERF, the shown in blue, has similar accuracy to the approach using GSO and the Backend Analytics system. This indicates that we are able to obtain similar accuracy without incurring the cost of computing the aggregate functions over the actual data. In addition, we see that we can outperform PRIM when the task involves multiple regions, as we suspect that PRIM converges into single regions. And we also see that for the density task, we were not able to tune PRIM properly, which might indicate that PRIM might be unsuitable for this kind of task. In addition, we show some of the performance results here, where we have an increasing dataset size from 100,000 to 1 million to 10 million, and we also increase the dimensionality size of the dataset from a single dimension to 5 dimensions. And we have a cutoff time set at 5 minutes, 3,000 seconds. So we evaluate each of the approaches under different settings, and if the approaches were not able to finish within 5 times, we would basically eliminate the task and indicate how many runs, how many queries, how many function evaluations, if you like, where we were able to perform within this time limit using the proposed approaches. So as you can see, SERF is relatively constant across all settings and does not exceed a couple of seconds. As we can see for naive, as dataset size and dimensionality increase, the method does not scale. And what's most important is that only 0.01% of function evaluations were performed for a dataset size of 10 million with dimensionality 5. In addition, using GSO with the Backend Analytics system, we see that it's pretty similar to naive, whereas dataset size and dimensionality increase, the method is no longer scalable. As we can see, PRIM is highly scalable. However, it starts to degrade as dataset size increases. And PRIM also assumes that all data are loaded into memory, which is also often not the case. That would be all for my presentation. Thank you for your attention, and I'll be glad to take any questions that you might have.
Okay, so thanks, Fotis, for the nice work. While we're waiting for possible questions on chat, I do have a question. So, actually, I see a question here. Maybe I'll just read this. So I'm wondering to know, is there any theoretical guarantees of your method?
Hello, can you hear me? Yes. So I would like some clarification with respect to this question, like theoretical guarantees as to whether the method converges to the interesting regions or something else.
I think the question is general, I guess.
Yeah, so well, I can answer it in a general way. So in a general way, there was no work to prove that the algorithm would always converge at certain positions, if that's what the commenter is asking. However, through extensive testing, we've seen that although the GSO algorithm is stochastic, so it converges to different positions every time, it will always converge as closely as possible to the regions that we've defined as interesting. I'm hoping this answers the question, but we can always take it offline to Slack or in the chat.
Okay, thank you very much for the answer. So if there are no questions, since we're a little short in time, I think we can move on to the next talk. So let me introduce our last speaker. Xinyang Yu is a senior staff engineer in Alibaba Group, has more than 10 years experience in computer architecture, design, and applied AI. And the title of the talk is Two-Level Data Compression Using Machine Learning in Time Series Database.
Hello everyone, in this talk, I will present our paper called Two-Level Data Compression Using Machine Learning in Time Series Database. I'm Xinyang Yu, the leader of this paper. This is the agenda of our presentation. Let's start with the background. Time series exists everywhere. Typical scenarios of time series database includes IoT and sensor monitoring, DevOps monitoring, real-time analytics, and so on. From the left chart DB engine ranking, we can see there are various time series databases, and their activity factor are increasing significantly in the past few years. What's the major task of a time series database? From the top level user view, it needs to handle lots of queries, analyze, and predict. For example, query the past month's NASDAQ composite index status. From bottom level system view, it needs to handle massive read, write, do compression and decompression, and apply downsample, aggregation, etc. In this example, to compute the index, it needs to process the stock information of a bunch of IT companies every second, and then perform operations like downsample and aggregation to get the final curve. Note that in most cases, the data structure to be handled is simply a pair of timestamp and value, each with 8 bytes usually. As we are stepping into an era of digital economy, IoT, 5G network, etc., the data of time series is exploding. How to store and process the data efficiently? A straightforward idea is to apply compression. Yes, after applying compression, we can safely print, improve transfer latency, and improve process performance. And then the question will be how to compress efficiently. There already exists a lot of nice compression schemes as we listed on this page. In general, they support a single mode or a few static modes to compress the data. Most use bit packing, good for compression efficiency. Next, we will introduce our two-level compression framework. We just introduced a lot of existing schemes. Unfortunately, each of them is only effective on a certain type of inputs. This figure shows an example of this case. You can see in the sub-figure D that different parts of data prefer different compression schemes. As you can see, in real-world scenario, a data usually contains different patterns. Therefore, we don't want to fix a single compression scheme to compress the data. We want to smartly choose an appropriate compression scheme on different parts of the data. And this is exactly the goal of this work. Before going to our solution, we have to introduce 3 important characteristics of time series data: time correlation, pattern diversity, and the data massiveness. According to data compression fundamentals, A data compression process consists of two stages. A transform stage that transforms data from one space to another, which is more regular, and the differential coding that uses various coding methods to represent the differential value of the transform. We define 6 transform primitives currently. Take near linear time series data, for example. If we apply delta of delta, the transformed data only contain a little information. The next stage is to encode the data with less space. Reference AMMMO, we want to do bit level packing. Almost all data is byte aligned in order to fit parallel computing well. 3 differential coding primitives are defined currently. Note, there are actual parameters to associate the coding. For example, byte offsets for offset mode. And in this case, when you use offset value 3, we can compress a 5-byte data into 1 byte. Come to here, a naive solution will be try all possible combinations for each data point and pick the best. Then a problem is metadata exposure. For each data point, we need to encode at least 2 byte metadata, and the overhead is a bit high. Raw data is 8 bytes, and overhead is 25% here. Look back to the time series. Actually, even though there are significant differences among each other, and the patterns may change inside the time series, but for most time series data, patterns can remain stable for a contiguous time range. Therefore, parameterized skin space is defined to solve the whole problem. We can use several parameters, 9 here in AMMMO, to represent all the time series. When looking into a detailed timeline, we figure out a proper skin space to represent it. Which only contains a few, for example, 4 compression skins. In point level, we only search the best one from these 4 choices, which keep it simple enough to achieve good throughput. Then, since most metadata is in timeline level, only 2 bits is needed per point, and the overhead will be only 3%. This slide illustrates overall framework of AMMMO. It mainly separates into 2 stages. In the top level, use algorithm to figure out a proper skin space. And in the bottom level, it finds the best skin from the selected skin space, and then perform the corresponding compilation. Obviously, bottom level compression skin selection is easy, but the skin space selection is a key and full of a challenge. Left is a rule-based skin space selection algorithm. It could solve the problem, but some obvious issues are: first, it imports metrics like benefit score are human-created, which may not ideal. Second, the logic has to be manually implemented. It can cost a lot of time to implement, debug, and maintain. Third, as we mentioned before, the primitives can be extended to fit other patterns according to the real-world scenario. We need an automatic and intelligent method to update the algorithm of skin space selection as well. Machine learning, or more specific, deep learning, has been proven to be very useful for many classification problems. And think about this skin space selection algorithm. Input a lot of time series data to analyze, and then output the proper value of these 9 variables. We can model it as a multi-label classification problem. And why involve reinforcement learning? There are three major concerns. First, it is not easy to create a sample with a label. Second, this is not a typical one-class problem. Very likely, many choices achieve the same best result. Last, but also very important, we need an automatic solution which works well with improvement on primitive tool, skin space definition, etc. This page shows the whole neural network framework. 32 points are taken as a basic block to process. We are using policy gradient-based reinforcement learning. In the training stage, a batch of n blocks, and each has duplicate copies, are fed into a 3 hidden layer network. We then pull the network result and generate a control parameter for skin space, calculate the compression ratio, and then use loss to do back propagation. About the loss function, the F part is a well-defined function on compression ratio. If a control setting achieves good compression ratio, it will be positive value, or else it will be negative value. HCS part is closed entropy to penalize probability. And the last is the regularization part to avoid conversion to local optimum. In the inference stage, first, just input a batch of blocks and get the final control setting per block. And then we apply statistical method to get the most frequent value as the final one for a timeline. Here are the result evaluation. In the dataset side, we randomly pick 28 time series from our platform on IoT and server scenario. Also, from a widely used dataset UCR, we pick the 8 longest time series. Note, we separate the dataset into A and B for ML, A for training, and B for test. In the algorithm side, well-known algorithms like Gorilla, AMMMO, Snappy are added. Since AMMMO is a two-level framework, there are various algorithms to do the top level skin space selection. Here, lazy mode is we directly set the parameter to a static value similar as Gorilla AMMMO. Random 1000 average random the parameters 1000 times and calculate the average compression ratio. Analyze. Use the rule-based algorithm by human craft. ML is a DRL version. Overall, AMMMO performance are illustrated here. Figure 7 shows the overall compression ratio compression. Gorilla AMMMO, which are designed for time series data, are better than Snappy. And we can see AMMMO is around 50% better than Gorilla AMMMO by average. Figure 8 shows the detailed compression ratio value per time series in test set A, almost the same trend as the overall conclusion, except U-wave, which Snappy performs very well. And figure 12 shows the compression efficiency. Since AMMMO is similar as AMMMO, which removes bit packing for better parallel computing, the overall performance in GPU side is great. In GB per second level, both in compression and decompression side. This slide shows the effect in the ML version view. Figure 10 illustrates the detailed compression ratio on validation test set. The ML version performs good, similar or slightly better than analyzed version, significantly better than lazy and random average versions. Table 9 shows the detailed parameter values among analyzed, ML, and random best. We can see ML performs good in the offset, major mode, etc. parameters. Conclusion. We propose a two-level framework for time series data compression. In detail, we present AMMMO definition. The results show that it achieves around 50% better compression efficiency and fits parallel computing well. Also, we designed DRL logic to do skin space selection. which is an automatic, intelligent, and efficient way. The last is reference, and thanks, and QA.
Okay, thanks, Xinyang, for the very interesting work. So while we're waiting for any questions to appear in chat, maybe I can ask a question. So this work is, I think, focused on compressing data. Do you also have plans on analyzing the data that's compressed? Do you see any efficiency issues on analyzing the time series data in compressed form?
Okay, that's a good question. Yes, we do have some analyze on the time series data. In that paper, we can see some data are more straight like a line, and something maybe triangle down and up. Yeah, they divergent a lot. Yeah.
Right. Okay, any questions from the audience? Okay, so I think we're a few minutes overboard, so sorry about the delay, but I'd like to thank everyone for participating in this session. So we're going to have a 25-minute break, and the next session, we're going to open the room 5 minutes before it starts. So thanks very much for your attendance today.
Thanks. Thank you, everybody. Thanks, Stephen, for chairing the session. I just wanted to remind Alan. Alan, you should stop the recording now.